In the next couple of examples, we're going to take a look at these trigonometric equations with exact solutions. And now we're going to talk about higher degree equations. So before we just had like cosine of x or cosine of 2x. Now I have this weird symbol notation over here. This reads as 2 cosine squared of x equals cosine of x plus 1. So I've increased the degree. And one thing to note is that cosine squared of x, that's just a notation for cosine of x, that whole function squared. And the reason why, just as a side note, why we use this type of notation is if I wrote cosine of x squared like this, now there's some ambiguity. It looks like I'm squaring x when instead I would need some more way to notate that I'm squaring the entire function. So that's why we use this little exponent kind of in between where the function word ends and the actual input begins. So this is just this notation that means this. We don't like that. So now that we've got that established, this is actually going to be kind of like a quadratic since I'm dealing with this second degree cosine equation. And one thing that might be a little intimidating is I'm looking at all of these cosines left and right. Well, let's simplify our lives a little bit. I'm going to do another u substitution. And I'm going to say, well, I want u to just equal cosine of x. And when I do that, I can substitute in, anywhere I see a cosine x, I could substitute in a u. So over here, instead of 2 cosine squared of x, I could say 2u squared. Since cosine squared of x is cosine of x times cosine of x, that's going to equal u plus 1. And now this is looking a little bit like a quadratic that I can solve. So let's get it equal to 0. 2u squared minus u minus 1 equals 0. And now I'm going to factor this quadratic. So I'll have 2u and a u. And it looks like I'm going to have a minus 1 over here and a plus 1 over here. All right, that's great. I factored this quadratic. I could solve for u. I could say u is going to equal negative 1/2, or u could equal 1. And that's all well and good, but I'm not solving for u. Like, really, there was no u to begin with. I want to solve for x. So now let's put our cosine of x back in for u. So that means that the sine, I'll take this first solution here. I'll say the sine of, I'm sorry, not the sine, the cosine. So now I'll take this actual equation here, u equals negative 1/2, and I'll substitute back in cosine of x. So I have the cosine of x equals negative 1/2. And let's just solve this right here first. So x could equal, when cosine of x is equal to negative 1/2, that's going to be in quadrants 2 and 3. So I'm thinking that's going to be a 2 pi over 3 and a 4 pi over 3. I'm going to add my period until I get up to 3 pi here. So this is like, let's think of this in terms of pi's over 3. This is equal to a 9 pi over 3. Okay, and so I'm going to add 6 pi over 3 to each of these solutions. So I'm essentially adding a period. So if I add 6 pi over 3, that's going to be an 8 pi over 3. That still fits. If I were to add a 6 pi over 3 here, that would be a 10 pi over 3. That's too much. So these are all the solutions that I'm going to get from cosine of x equals negative 1/2. Let's take the second solution here, when u equals 1, and we'll substitute back in cosine of x equals 1. That's only going to happen in one place, and that's when x equals 0. But I guess I should say it also happens at 2 pi if I were to rotate all the way around my unit circle. And the next time that's going to happen is going to actually be at 4 pi. That's outside of my restriction, so these are really the only solutions for this scenario. So let's put it all together, and now let's kind of package all of my solutions from the first equation and from the second equation. And I'll do that right below here. So x can equal all of these things: 0, 2 pi over 3, 4 pi over 3, 2 pi, and 8 pi over 3. And again, we could always check this using the graphing calculator. I could graph one y equation here and one y equation here. This could be y1, this could be y2. Look for where they intersect. And I should get these as decimal approximations. But that's a good way to check your work to see how well you did. It's a little bit trickier, but as long as we just kind of think of this as it's a quadratic, and then we apply some basic trig equations at the end, it's really all the same. So why don't you try this one, pause the video, give this one a shot. We've got another trig quadratic, use those U substitutions, and then consider your domain restriction. So pause the video, give this one a shot. All right, and here's my final solution here. My workings out are below. I came up with these 5 possible solutions, and hopefully it went okay.